So, hello and welcome back to this module 47 of the manufacturing systems technology. We were at this problem and we were trying to evaluate the number of Kanbans in the situation given in this particular problem statement, where there was a production of a certain item and the demand was given per month, 20 working days month was assumed, and we wanted to calculate what is the number of Kanban given the policy variable, given the number of items in one bin, and also the production lead time, which is the Kanban waiting time and the production time. So, we calculated the number of Kanbans to be 7 in this particular case, and now this next situation is that suppose the company has stable production environment and the policy variable now is fixed as 0, that means there is no overstocking. So, obviously in that event, if the alpha here, which was about 40%, is now reduced to 0, so alpha becomes equal to 0. So, the Kanban numbers would also reduce to 0.5 divided by 50, okay. So, it is basically only 1 multiplied. So, this would actually make it about close to 5. So, we are having 2 less Kanbans, because we want to now only operate at the demand level and there is no overstocking whatsoever. So, essentially you are producing in a manner so that by circulating 0 to bins lesser, the process still gets balanced. So, the overall stocking is reduced to about 100 components, okay, by about 100 components. So, that is how the you can really estimate what happens in case of a change of policy. So, obviously these 100 components which were there earlier were because you wanted to keep a 40% additional stock at every level. Now, you just remove that, and so why I am saying 100 is because, as you remember, that every bin contains 50 parts, right. So, 2 less bins means about 100 components less at which you can still operate. The other problem statement that has been given is that supposing in the situation what would happen to the if the lead time is increased by 1 day to 1 day because of the labor shortages and failure of machines, okay. So, in that event obviously you had a policy variable 40%, let us assume no changes in this condition, and you want to supply and balance the number of Kanbans y. So, here it will then come out to be 500 the demand per unit day times of the lead time. Now, the lead time has been sort of increased to about 1 day. So, lead time is increased to 1 day. So, the TW plus TP becomes equal to 1, and then you have the policy variable which is still operating at 1.4, and you divide it by the number of containers here. So, this comes out to be again about close to 14 Kanbans. So, you can see that you have to operate at double the level. So, operate at double the level of Kanbans as the lead time is increased to double. So, whatever model you are proposing actually works out very well here, that now if the lead time is reduced, is increased from 0.5 days or half a day to a single day because of whatever issues, the Kanban should also get doubled, because then you are accommodating for a greater period and you have to buy more stock and keep more stock in question, okay. So, the stocking area gets increased by 7 bins, about close to 350 components more, and that is how so the inventory level goes up because of that. And this is something that you should record very well, and this is something that you should monitor. You cannot obviously starve a process by not feeding it material just because you are implementing lean manufacturing. But if you can have a record on a monthly basis of how many such components are there where the overall Kanban level has gone up, and you have to create a situation where you are having a higher policy variable. Okay. So, those are the most problematic areas which are in direct view of the management, and you can do something so that the processes and the way that the supplies etc. are happening can obviously improvise, and the lead time for the Kanban can reduce because of that. The moment the lead time again gets reduced, you are back to the normal level and you are operating at the leaner level. This has to be done, mind you, for all the inventory that is involved in particular manufacture of a certain product. Okay. So, the next situation again is a situation where the policy variable is changed to about 30%, and the lead time again reduces because of some process improvements etc. to about 0.25. Now, it is quarter of a day that the lead time has been reduced to. So, obviously, in that level the Kanban will go down further. So, 500 into 0.25 times of 1.3 at which it operates now divided by 50 makes it about 3.25. Okay. So, it is going down from the 7 Kanban level which you had earlier obtained to 3.25. Actually, you should record this as 4 Kanbans, because obviously you cannot understock the situation. So, it is a good idea to estimate on the overside. So, 3.25 gets converted into about 4 Kanbans. So, you are having at least 3 Kanban reduction because of this improvement that has happened, leading to the reduction in the lead time to about quarter of a day. Okay. So, obviously, such improvements are what the management practice should be to get into, and the more the improvements can be suggested, the better it is in terms of overall line balance using Kanban techniques. Okay. So, that is how you basically try to understand the whole deterministic estimation of the Kanban. When we are talking about subassemblies, for example, let us say there are 2-part subassemblies which has the individual production and withdrawal Kanbans, and then they are matching together to make one product assembly. There would be a slightly detoured scheme of things where there are many values which are involved. So, I will do one example where, or one case study where such a thing is such a situation is available, that you have 2 or more components going into a subassembly, and that stage how do you do Kanban, and then we will slowly move on to the next module, which is about the cost analysis into picture. Okay. And how to make the estimation of the Kanban probabilistically. So, let us look at the subassembly module. Here is such a case which involves the subassembly level Kanban planning. Let us say you consider a manufacturing process which produces the product Z in a company, and the Z is assembled from 2 parts by subassembling these 2 parts X and Y to each other. So, Z comprises of 2 sub parts which are subassembled into one another to make the Z. Okay. And a schematic layout depicting the preceding stage, the staging area, subsequent stage, and the flow of the production and withdrawal Kanbans is given in this particular figure here. Okay. So, you can see that there are 3 work centers principally involved in this particular process: the work center for the production of the part X, the work center for the production of the part Y, and they are subassembled into a subassembly center Z, which comprises of the subassembly of X and Y, and there is stocking area separately given for the component X and the component Y close to the assembly center, and there can be a withdrawal cycle for X and Y simultaneously to go to the assembly center so that Z can be produced, and there can be a production cycle as illustrated earlier between the work center X and work center Y, which would feed the stocking area for X and stocking area for Y. So, that is how the whole line balancing is done in this particular case. So, we need to determine the production and the withdrawal Kanbans. I will give you some of the values here related to the lead time or the policy variable or the demand per unit time, so on and so forth. And so, we have to create, instead of a balance between one process to the staging area to the stocking area to the next process, we are creating between 2 processes, 2 stocking areas and 1 final process based on that. So, that is the only diversion that we are having in subassembly level Kanban planning. So, this let us address the first part of the problem statement here, how to determine given the values here. Let us look at the values. So, at the assembly stage, the demand per unit time, which is mentioned in per unit days, is 2000 for X, okay, and 800 for the part Y, and the lead times which are available for the part X and Z for planning the assembly stage is 1 day and half a day respectively. There are two policy variables, 0% and 25% level, which is operated for X and Y respectively, and further the container capacities have been defined as 100 parts per container of X and 50 parts per container of Y. Similarly, at the manufacturing stage, which we also know as center, which would be needing really the production Kanbans. Okay. So, it is a back end process manufacturing stage. So, let us now define it here. So, this side is really the assembly stage that we are talking about, which I have just described before this, and this side here is the manufacturing stage, and the values are given in commensurate manner based on different stages. So, you can see that the withdrawal stage is the assembly stage and the production stage is really the manufacturing stage. So, that is how you plan the production and the withdrawal Kanbans. So, this assembly stage Z would mean the withdrawal Kanbans, and the manufacturing stage would typically involve the production Kanban. So, given this value, we want to find out the different levels of the withdrawal Kanbans and the production Kanbans in cycle, so that there can be a proper process balance. So, let us determine the withdrawal Kanbans first. The lead time used for determining withdrawal Kanbans is the time it takes the part to travel from the preceding stage work center to the subsequent stage, which is Z. So, therefore, just write the statement here that the lead time, which is given in this particular portion of the table here, okay, is really the time it takes for the parts to travel from preceding stage work centers, which are actually the manufacturing stage. Okay, I can call these centers X and Y, to the subsequent stage, which is the Z. Okay. So, the number of withdrawal Kanbans for X, for example, would be the demand per unit day, which is 2000 times of the lead time, which is 1.0 times of the policy variable. So, 1.00, again we are operating in a very lean 0% inventory level, divided by the container capacity. So, that comes out to be 20 for X, and for Y it comes out to be again the the demand units per day divided by, or times of the lead time, which is half a day, times of again 1.25. we are operating at an alpha value of 25% divided by the container capacity in this case, which is 50. Okay. So, that brings a value of 10 respectively. Okay. So, for X the number of withdrawal Kanbans is 20, for Y the number of withdrawal Kanbans is 10 respectively. So, now we determine the production Kanban level. So, let us say part B, determining the production Kanban level, meaning thereby we need to use the values towards the lower part, the manufacturing stage part of the table. Okay. And here for the lead time, there exists a similar definition. So, we call that the lead time for the production Kanban is the time it takes to manufacture and transport the parts X and Y to stocking area. Okay. Just as in the withdrawal case we had seen, it was really related to the amount of time taken by the parts X and Y to go from the previous stage, that is the stocking area, to the assembly center Z. And in this case, in the case of production Kanban, it is just how much time it needs to manufacture and transport this part X and Y to the stacking area. So here again for X, if we look at individually, the demand per day is about 2000 and lead time is about half a day, alpha is 0.20, so 20% level. So the X becomes equal to 2000 times of the lead time for X and the production side times of 1.20 operating at 20% level of the policy variable divided by 1000, and this comes out to be equal to about 12 units or 12 containers as the Kanban level. And similarly for Y, we will have a similar calculation starting with 800 demand per unit day times of 1 day lead time times of policy variable set at 0%, okay, divided by 50, which makes this about 16, okay, respectively. So for X and Y, you have 12 containers in one case and 16 containers in another case, and so that's how you can plan the number of Kanbans, okay, into picture. So since the lead time is basically defined by this proximity of the assembly stage with respect to the manufacturing stage, the second part of the problem involves a little bit tricky situation, that there is a reorganization of the company, because of which the assembly stage has been shifted now to another place, and the new lead time to travel between the new location in the existing place and the present plant location is about 4 days. So the lead time has really increased for both X and Y components from the earlier level of the 1 day and half a day respectively to now about 4 days. So naturally the withdrawal Kanban would increase, because now your whole idea is that this stage is going far away, okay. So this is 4 days away, and the withdrawal side are now having increased leads because of the proximity issue, because of the assembly stage moving distant, I mean to a greater distance from the work center, and so therefore obviously the stocking area size has to go up, because it can accommodate that way the manufacturing plus the lead time constraints which have been imposed on the system, and it should be able to still create a flow or a balance between the manufacturing stage and the succeeding assembly stage, okay. So therefore in this particular case the Kanban level will simply bloat up because of this. So the withdrawal Kanban level will definitely be different in this case. So withdrawal Kanbans now would be calculated for X to be equal to the demand per unit day, which is about 2000, times of the lead time now, which is 4, times the policy variable, which was 0% earlier at this particular stage for X, divided by the container capacity. So this becomes 80, and similarly for Y, again it's 800 units per day demand, and then you have a 4-day lead time, and then policy variable of 1.25 divided by 50, which is also again 80. So therefore if you see the increase in the withdrawal Kanbans from earlier 20 and 10 level, so there is about a plus 60 increase in the X withdrawal Kanban level, and about plus 70 increase in the Y withdrawal Kanban level from the earlier recorded value of 20 and 10. Okay, so let me just write this here 20 and 10. So it obviously means that you're creating an overstocking situation to sort of mitigate the constraint, additional constraint put on the system by increasing the lead time. Okay, so that's how you do the Kanban level planning at the subassembly stage, and it is very important for me to mention that whether it is a just a one stage process like a preceding stage, a stocking area and a succeeding stage, or many such stages process like you saw in this particular case, two stages are converging into one stage, and there may be a case where 5 such subassembly units are getting assembled together, or there may be a chain of such subassembly events. All you need to do is to sort of meticulously balance the production side and the withdrawal side for individual components, keeping the individual stocking areas in question to maintain the balance or harmony of the flow of the product. Okay, so that's what the whole concern is for designing a system which would have a perfectly harmonious Kanban balance. We'll now look at a little bit different side of the story, which is about the just-in-time manufacturing and an understanding of what really this Kanban planning would have to do with just-in-time manufacturing. So obviously, the jet manufacturing is often understood to mean a manufacturing system with a lot size approaching unity, meaning thereby that only one part is needed at a point of time, you have to supply that only one part to the system. Obviously, it is too far away from the realistic situation. You really have to do a lot of homework in order to create that situation where the container size of the Kanban is operating at a level of n equal to 1. Okay, so it's important to understand the conditions under which this goal may be achieved, and the answer may come directly from the classical economic production quantity inventory model. Now this is something which has really emerged from the MRP or the materials requirement planning. I'm not going to go into the details of how you arrive at this economic order quantity or the economic production quantity for the inventory model, and accordingly the total variable cost consisting of a setup and holding as a function of economic production quantity Q is also provided. So let's say I just want to sort of go ahead and see what is the kind of total cost which is involved. We have a situation here where A is supposing the setup cost of the equipment of the plant machinery, and C is the unit cost. So it's the sort of the price of the item or the inventory in stock. Okay, and I is the annual inventory carrying cost rate D is the demand rate, P is the production rate. So all of this is per unit time. Please take a note of all this. Okay, and then Q is the economic production quantity that we are talking about. So if we look at the total cost of the inventory carrying which comes into the system, it's obviously related to the setup cost. So if D is, let's say, the demand rate and Q is the one production lot size or one production quality. So the number of times that the equipment needs to be set up is really D by Q, assuming that there is a complete variance between one economic lot and another economic lot. So that's how number of times you can associate, where you can reset the equipment before starting a production process, and obviously the setup cost comes as A. So the total cost which gets compounded is A times of D by Q. And obviously if you look at the annual inventory carrying cost rate, the total amount of inventory carrying cost would really depend on the difference between the production and the demand percentage. Okay, and that is sort of multiplied by the unit cost, of which percentage is the annual inventory carrying cost. So IC is that particular unit cost times the the average economic quantity, which is q by 2 in this case, times of p minus d by p, which is the percentage sort of excess material as a percentage of the overall production rate. Okay. So, if P is the production rate, D is the demand rate, obviously the production is more than the demand, and so the question of holdage comes into picture, or inventory carrying comes into picture. So, I am really not getting into how to get into the mathematical derivation of this particular cost equation. It comes from directly from the economic order quantity estimation model of MRR. But here the idea is that the total cost can now be related to the setup side, where A d by q is the setup cost, and the inventory carrying cost rate side, which is defined as I c q by 2 times of 1 minus d by p. Okay. So, having said that, the economic quantity, or the optimal, let us say, economic quantity, which will be formulated here, we call it q star, okay, which minimizes the cost function can be obtained by just differentiating the total cost with respect to q. So, this can be calculated as minus AD square AD by q square plus IC by 2 times of 1 minus d by p, and equating that to 0. And so, the economic order quantity q star comes out to be equal to twice AD divided by IC 1 minus d by p. Okay. So, that is how you can define the total economic production quantity. So, if I were to really plot this cost function as a contribution of the total setup cost as well as the annual inventory carrying cost, the total amount, the way that we can plot it. So, let us say we make a plot of the holding cost as well as the setup cost as a function of q. Okay. So, you have cost on the y axis and q on the x axis. So, obviously, we are talking about a condition of a minima of this particular cost corresponding to the value q star. Okay. So, this total cost is minimized here, and if I really were to plot the cost function, which is defined again as A d by q plus I c q by 2 times of 1 minus d by p. So, the inventory carrying cost, if we look at, is the annual holding cost, or the inventory carrying cost is really the linear component. Okay. And the total cost coming because of the annual setup cost is a sort of 1 over q relationship, which sort of comes like this, and I can just split this up into the annual holding cost, the linear function, okay, and the annual setup cost. So, obviously, while the holding cost increases the cost function as a linear function of q, or with increasing production lot sizes, the holding cost goes up, the setup cost comes down because of increasing lot sizes, and so there is a sort of a harmony between both of them, and they would have the maximum effect on each other to minimize the cost function at a certain point q star. Okay. So, obviously, if I were to pull this back, or let us say create a situation where these total costs, okay, come down more and more, the q would shift to the left, okay, which would reduce, which would probably try to sort of reduce the overall cost. And the whole idea is that for a given demand and production rate, if Q can really go to the JIT level, okay, which is actually operating at a single stock, okay, or maybe corresponding to one item as a only inventory which is involved in this whole process, the overall setup cost in that event should be the minimum. Okay. So, for this economic lot size to approach unity, and if we want to really minimize the cost function, the value of A has to go to the lowest level. So, in fact, a ideal situation is that if A is equal to 0, that means there is no setup cost, then there will not be any contribution because of the lower value of Q. Okay. And we can operate at the almost Q equal to 1, which means that the number of times the setup is needed almost is going to be same or commensurate with the rate at which the demand is happening. Okay. So, for every product you have a setup, but that setup time is 0, meaning thereby there is really no setup which is needed. Okay. So, in that kind of a situation, which is a one in one out flow of system, you can really maintain the JIT level. But however, the truth is that there is a finite amount of setup cost which is involved, and so therefore, it is really a dream to shift to Q equal to 1 level or the economic order quantity level. So, having said that, I think we are more or less towards the end of how you can envision JIT with the total Kanban, overall Kanban level. I will just quickly discuss a few more important points which I felt is sort of to be discussed in this part of the course before going into the probabilistic estimation of the number of Kanbans, which would be probably in the next module. Okay. So, here I would say that apart from the regular production and withdrawal Kanbans, there are many other type of Kanbans which are available in the system. So, one of them is called signal Kanban, and this is probably it comes into existence when we were talking about a large setup time, let us say in a press shop for example. You need to set up the dies, etc., and it takes a humongous amount of time to do one setup, and there the condition of that economic order quantity Q of certain size comes into picture, for which we have just done the analysis or completed the analysis. So, one of the important conditions for implementation of JIT with Kanbans is to have low setup times relative to processing times, but this is not always the case, and so therefore, you have to use a technique where instead of a one by one withdrawal of the item, there is a lot by lot withdrawal of the item, and so that actually is known as a signal Kanban. Okay. So, signal Kanban is really something where there would be the placement of the withdrawal card in a manner so that rather than moving one bin at a time, it is moving a lot of certain number of bins at one time. Okay. So, that way you can actually increase the queue and reduce the setup cost, as you had seen in the earlier analysis. And so, even if there is a finite amount of setup time, associated setup cost, you should be able to operate at a certain basic minimum of Q, where the total cost again is going to be minimum because of that. So, that signal Kanban. Okay. So, instead of a one by one, you have a lot by lot movement. There are some other exigencies which are used, for example, supposing there is a defective unit which is produced at a work center. So, you have to really produce an emergency Kanban there, which is actually not a process imbalance, but in order to maintain the flow, and this has to be the decision has to come from the highest level of the company when you are trying to induce this emergency Kanban into picture. Okay. So, there are many other uncertainties like machine failures, etc., which would result in issuance of an emergency Kanban, where maybe an over production in a particular shift, or maybe a planning in a manner so that there is an extra number of hours which are involved because of the machine breakdown, so that the system flow is harmonized and it gets balanced. Okay, so that's emergency Kanban. And then obviously the other one is through Kanban, which is really the situation when the stations are very close to each other. There is no need of any stocking area, so it is almost a one in one out kind of a system. So that is another kind of Kanban which is envisioned, and these are the different other Kanbans apart from the production and withdrawal Kanban that you learned towards the beginning of this lean manufacturing topic. So with this I would like to close this particular module, and we will sort of go into another very critical area of how to probabilistically determine the Kanban level in such a in a situation where there is an associated hold up and a shortage cost based on if the Kanbans are at a level which is higher than the total demand or lower than the total demand respectively. So we will do that in the next module. Thank you.